Hi, welcome to CEE122 recitation 5, and this recitation will go through the homework solution for problem for the homework 5. And this is the new recording because the last one, due to some technical issue, the voice is not recorded. So this is just to recover that technical mistake. Okay, so let's see the first problem, 4.28. And in this problem, it gave us the velocity of the water flow in nozzle, shown is given by the following expression in this equation. The v is velocity in feet per second, t is the time in second, and x is the distance along the nozzle. And L is the length of the nozzle, which is equal to 4 feet. I just write that information down here, 4 feet. And the x is equal to 0.5 L, and t is equal to 3 seconds. Okay. And the question asks us what is the local acceleration along the central line and what is the convective acceleration and also what is the convection acceleration. And assuming that is quasi one-dimensional flow prevails. So this problem is actually testing us the definition of the local acceleration and the definition for the convective acceleration. So let's just write down what is the definition for the local acceleration for part 1. The local acceleration is equal to partial v divided by partial t. Okay, so that is the definition. And according to this definition, and we have the equation for the velocity, so we can just take the partial derivative with respect to t. So partial v divided by partial t is equal to this, and I just copy that equation down here, divided by L to the power of 2. Okay, so because the t is here, so other variables and numbers are just a constant toward this t. So the derivative will be 1 minus 0.5x divided by L to the power of 2. Okay, and we know that x is equal to 0.5 L, right? And we know L is 4 feet, so this x is actually equal to 2 feet, right? So you can just plug this L and x into this equation, then you will get the value equal to 3.56 feet per second square. Okay, so similarly, for the convective acceleration, we need to know the definition of the convective acceleration, which is equal to v times the times the partial v partial x. And if you want to know the entire derivation or explanation of what is the local acceleration and convective acceleration, I will refer you to the textbook. And here we just focus on how to solve what is the critical knowledge we need to know to solve the problem. Okay, so we have the equation here, and the things that we need to solve is this partial v and partial x, and that's right here, partial v partial x. Again, I will copy the equation down here, but with a small I just rewrite the equation a little bit. So I put this bracket here, parentheses here, from the denominator into the numerator. And remember that if we want to do that, we just need to add a minus sign on the power part. Okay, so this is 2t times 1 minus 0.5 x divided by L to the power of minus 2. Okay, and now we want to apply the chain rule to calculate this derivation. So 2t is the constant to, the term that have this x involved is actually this part. So this 2t become a constant. So we just write this 2t down first because the partial derivative to x will not affect this 2t. Okay, then we will apply the chain rule. We first take a derivative to this entire term here. Move the minus 2 down and times 1 minus 0.5x divided by L to minus the power of minus 3 because minus 2 minus 1 is equal to minus 3. Okay. Then applying the chain rule, now we want to take the derivative of x to each term inside this parenthesis. So the constant take derivative is equal to 0, and the second term, the remaining part is 0.5 divided by L. Okay? Cool. So if we reorganize these parts a bit, we times these with these, and we'll get 2t divided by L times 1 minus 0.5x divided by L to the power of minus 3. Okay, so these two terms will be this part. Okay, now we plug this equation back to this convective acceleration. So we know that the v is 2t 1 minus 0.5x divided by L to the power of minus 2 and times the partial x that is equal to 2t divided by L times 1 minus 0.5x divided by L to the power of minus 3. Okay, then we organize these into 4t squared divided by L, which is this term, and we can combine the rest of the two terms into 1. That is 1 minus 0.5x divided by L to the power of minus 5, because here is minus 3. Okay. And you know the x, you know the L, and you also know the t according to the information provided by the problem. So you plug those numbers into this equation, then you will get the solution is 37.925 feet per second square. Okay, so this problem is relatively straightforward. If you know the definition for the local acceleration and the convective acceleration, and know how to take a partial derivative, then this problem should be easy for you. Okay, now let's move on to the next one. The problem says the water stands at the depth of the 6 feet in a vertical pipe that is open on the top and closed at the bottom by a piston. What upward acceleration of the piston is necessary to create the pressure of 8 psig immediately above the piston? So here we have the pressure involved, and we want to know the upward acceleration, and the acceleration is somehow related to the force. So when we want to combine these two together to build up the relationship between pressure and force, we think we will come up with the Euler equation. So let's first write down the Euler equation. See how we might be able to apply this equation to help us solve this problem. So the Euler equation, according to your textbooks, looks like this. Am I not going to derive this Euler equation? If you're interested in that, I also refer you to the textbook. Here, we just use the end result of this equation and apply it to solve this problem. So it says that the partial derivative along the straight line of this term, pressure plus dou z, is equal to minus dou times the acceleration. And in this piston, we define the straight line is vertical, is vertical in this figure. Okay. So we can we can solve this derivative using the difference between the 2 points to approximate it. And to that, we will define these points on the top of the piston as the point 1. And these points at the surface of the water is point 2. And what we know about this point 1 and point 2 is that the pressure at the point 1 is equal to 8 psig, as given by the problem. And the pressure at the point 2 is equal to 0 because it's already open to the atmosphere. So that's why the pressure is equal to 0. Okay? And we also know and we can define the detent for this problem to be at the level of point 1. Okay, so Z1 is equal to 0 and Z2 is equal to 6 feet. Okay. So let's rewrite this Euler equation into a difference form. This will be minus delta. Instead of the partial derivative, we use the delta notation, which calculates the difference between 2 points of P plus dou Z is equal to dou AS times delta X. Okay. And you might wonder why we have this delta S here. Remember that if this delta P plus dou Z divided by delta S, and when the delta is really small, then it's equal to this partial derivative. Okay, and we just move this denominator in to the right hand side of this equation. That's why we have this delta S here. Okay, so that just expand this equation into 0.1 and 0.2. So these will be minus P2 minus P1 minus gamma Z2 minus Z1 equal to rho AS delta S. And we know the P2 is equal to 0 and P1 is equal to 8P SIG. So we can further plug in those values. 0 minus 8 PSIG, and we will convert the units into inch and feet. So we times this unit conversion term, 144 inch square divided by feet square. Okay, and we have the second term, that's gamma. The gamma is equal to 62.4 pound per cubic feet, and rho is equal to 1.94 slug feet. Okay, this is the two constants that we use in this problem. So the gamma is 62.4 times the Z2 minus Z1, that is 6 minus 0, and will equal to the rho, which is 1.94 times the acceleration and times delta S, and the distance of the difference between 0.1 and 0.2 is on the straight line, so this delta S is also equal to 6 feet. Great. So according to this equation here, the only unknown is this acceleration. Therefore, you can easily calculate the AS is equal to 66.8 feet divided by square root of second. Okay. So when you see the question, you analyze what kind of variable that you get, and you try to come up with an equation that can create a relationship between the variables that mentioned in the problem, and use that equation to solve the problem. Great. Now let's move on to the next one. So in the problem 4.37, a liquid with a specific weight of 100 pounds per cubic feet is in a conduit shown in the figure here. This is a special kind of liquid that has zero viscosity. The pressure at point A and B are 170 psf and 100 psf. Let's write that down first. So the PA is 170 psf and B is 100 psf respectively. And which one is more which one of the following conclusions can one draw with the certainty? Okay. So, in this problem, for the option A and B, it asks about the information for the velocity, and the option C and D is it provides the information for the acceleration. But again, when we have the pressure and what equation that we might be able to use to gain the information for velocity and acceleration. Yeah, so we just continue our momentum from the previous question that we have the Euler equation here. So what Euler equation can provide us? Let's see. The Euler equation again, it look like partial L of P plus gamma Z and is equal to Rho L. Okay. So we know the P is given by the problem. We know the Z because we have the angle 30 degree here. So the Z here, the Z here is 2 sine 30 degree. Okay, so we also know that, and though it's just a constant, so we know the information for the acceleration. And there's no other information that we can get to, derive the velocity of the fluid in this tube. So now we can cancel A and cancel B. So can we further answer whether the acceleration is positive to the L direction or the negative to the L direction? And let's see if we can calculate that, okay? Let's first put this partial derivative in for P and the gamma times Z. So we have partial P, minus partial P, partial L, minus gamma partial Z partial L. That is equal to Rho times LL, and partial P divided by partial L is equal to PB minus PA divided by L. This is 100 minus 170 divided by 2. That is equal to minus 35 lb per cubic feet. Partial Z and partial L. Partial Z can be seen as this part, and L is this part. So this is equal to sine 30 degree. Okay. So we can further plus those values back into the equation. So it's like 35 minus gamma, and sine 30 is equal to 0.5 times 0.5. And the gamma here is 100 because the problem tells us the gamma, the specific weight, is 100 lbf per cubic feet. Okay, and these will equal to Rho times AL. So we know this is equal to 15 minus 15 equal to Rho AL, and we know that Rho is a positive number, so the sign for the acceleration is negative, right? Because of minus 15. So AL, what we can conclude is that is negative. This is the information with the certainty. Therefore, we should choose the option D. The acceleration is in the negative L direction. Cool. So let's move on to the next one. The problem 4.43, an engineer is designing a fountain as shown and will install a nozzle that can produce a vertical jet. How high, which is this h, will the water in the fountain rise if the velocity at this nozzle is 26 meters per second as h is equal to 0? So v is equal to 26 meters per second. And for this problem, we'll apply the Bernoulli equation. So the Bernoulli equations show you the equivalence of 2 points which have these few terms. P2 plus V2 squared plus C2. And again, if you want to see the detailed derivation of the Bernoulli equation, please go through the textbook. They have a thorough derivation for this equation. But here, I'm going to teach you how can we solve the problem by using the Bernoulli equation. So similar to what we have applied the Euler equation, we will need to define the 2 points that we want to apply to the Bernoulli equation. And we define the points at the nozzle as point 1 and the surface of this jet as point 2. Okay, so we will need a variable for the pressure, the velocity, and the height. So we first define the data at this nozzle as z equal to 0. So we know that z1 is equal to 0 and z2 is equal to h, which is the information that we want to solve. And what about pressure? So P1 and P2, because the water are already exposed to the atmosphere, so the pressure are both 0 for point 1 and point 2. How about the velocity? The velocity at point 1 is already given by the problem, that is equal to 26 meters per second. And the velocity at the highest points of this jet obviously is equal to 0 because it already reached the highest point. Yeah. So we can use the information that we show here to simplify the Bernoulli equation and then solve the h, which is z2. So let's first cancel the pressure term, and z1 is 0, b2 is 0, these terms are all 0. This is v1. So the simplified equation is v1 squared divided by 2g is equal to z2. Plug in the number, v1 is equal to 26 squared divided by 2g, g is 9.81 meter per second square. So 9.81, and that is equal to z2. That is equal to h. So this gives us that h is equal to 34.5 meter. Okay. So after you know what is the Bernoulli equation and you know how to define point 1 and point 2 and their corresponding information for the height, pressure, and velocity, then you can apply that to simplify Bernoulli equation and solve this problem. Okay, let's move on to the next one. The problem 4.44. The tank shown is used to pressurize the water fertilizer solution for delivery from a sprayer. The tank is pressurized as P equal to 15 kappa. The height of H is 0.8 meter, and what is the velocity of the fertilizer at the outlet? So we want to find this velocity at the outlet. So again, in this problem, we will also apply the Bernoulli equation. Let's first write that down. P1 divided by gamma plus V1 squared 2G plus C1 equal to P2 divided by gamma plus V2 squared divided by 2G, the velocity term, and plus C2. Cool. And let's first define the point 1 to be the surface of the water. And point 2 at the point of the outlet. Right. And again, we will define the datum at this point 2. This is equal to 0. So the P2 at the outlet, because already exposed to the atmosphere, so the pressure will be 0, and the velocity is the variable that we will solve, and Z2 is equal to 0. Is at the datum. That's and for P1, the pressure is already given. That is 15,000 pa. Okay, this. And Z1 is equal to 0.8 meter, as shown here. And the velocity is 0, because we assume that the width of this tank is much larger than the outlet, so the velocity can be ignored in this case. Then we will use those information to simplify this equation. V1 is 0, Z2 is 0, P2 is 0, so the simplified equation looks like this. Okay, now we can plug in the number. C1 is equal to 0.8, V2 is the variable that we will solve, divided by 2G. And gamma is equal to 9790, and G is equal to 9.81. Okay, so we reorganize this equation to isolate this V2, and it will look like this. 2G times 150,000 plus 0.8. Plug in the G and gamma. 2 times 9.81. We get 6.76 meter per second. Okay. So the entire problem solving logic is the same as the previous problem. You apply the Bernoulli equation, you define point 1 and point B, and you identify the corresponding information for these 2 points, and then use them to simplify the Bernoulli equation, and you should be able to find the variable that you want to solve. And in this case, is the velocity at the outlet. Okay. Yeah. So here come to our last problem for this week. The problem 4.45, water flows through a vertical contraction section. Piezometers are attached to the upstream pipe and minimum area section as shown. The mean velocity in the pipe is V equal to 5 feet per second. The difference in elevation between the two water levels in the piezometer is equal to 6 inches. The water temperature is 68 Fahrenheit. And what is the velocity? What is the velocity? At the minimum area. Okay, so similarly, we will need to apply the Bernoulli equation. However, this time I'll write the Bernoulli equation in different form in order to apply the information from the piezometer. So basically, what I'm going to write will just move this gamma from the denominator into the numerator. Okay? So it will look like this. P1 plus gamma Z1 plus Zo V12 P2 plus gamma Z2 plus Zo V2 squared divided by 2. And again, we will define the 2 points for comparison. This is point 1, this is point 2. So this V2 is the variable one we want to solve, and this V1 is already given by the problem. That is equal to 5 feet per second. Okay. And we can reorganize this Bernoulli equation into this form. That's the Zo V2 squared divided by 2 is equal to Zo V1 squared divided by 2 plus. This is a critical step that you should write the equation into this form in order to apply the piezometer's information. Minus P2, okay. Comma Z2. And the term here is the information can be provided by the piezometer. Okay, so the difference of these last 2 terms is equal to gamma delta Z. Okay. So let's further organize these things. Though V2 squared divided by 2 is equal to plus Zo Z. And let's isolate this V2 variable. And let's cancel this Zo to here. Cancel these 2 times 2. Okay, so this will be V1 squared plus delta z to so, and let me rewrite this. So gamma divided by zo is g, because gamma is rho times g. So this becomes 2g delta z. Cool. And the v1 we already know is 5 feet per second, and plus 2g in the feet unit is 32.2 feet per second square. So 32.2, and delta z we already know is 6 inch, which is equal to 0.5 feet. So this is 0.5 because we use the unit in feet. That's why we need to convert the inch into feet. And then after you use your calculator to type all those numbers out, then you will get that the V2 is equal to 7.56 feet per second. And then we solve this problem. So essentially, in the last 3 homework problem, what you need to know is what is the Bernoulli equation, how to define point 1 and point 2, how to use those information at the point 1 and point 2 to simplify the Bernoulli equation, and then you should be able to solve the information that you need using the simplified Bernoulli equation. Okay, so this is the end of this recitation, and I hope you do well in your quiz for this week. See you.